talk not much about multi-electron atoms, but I don't really have a lot to say about them because what we learned about hydrogen applies to all of them. It's just things start to move around a little bit when you add extra electrons. So I'm not going to really talk about the spectroscopy or the energy level structure of multi-electron atoms, but I want to introduce to you a very key problem in chemistry, which is it's really hard to do quantum mechanics on things that have more than one electron. Right? And the helium atom will be a great example of that. It was so easy to, well, it wasn't easy, but we could write down an equation for the energies and the wave functions of hydrogen, no problem. Right? We have exact solutions for everything, calculate whatever we want about hydrogen to exact precision, but then we get to helium, and it all falls apart. Right? We can write down an equation, we can write down our Schrodinger equation for the helium atom, we can describe all the physics, but then when we go to do the solution, when we go to solve the equations, you can't. There's not a solution. So I kind of want to introduce that problem to you and set the stage for when we get the molecules where we have lots of electrons. And we have to come up with strategies on how do we calculate anything if we can't even calculate a system of 2. How can we calculate a system of 10? So we're going to have to come up with ways to approximate things and look at things from an approximate point of view. All right, so we're going to have to come up with guesses, if you will. And so we'll do some of those guesses today for helium. But before we do that, I want to finish up what we talked about last class, right, which is this idea that atomic states can be perturbed by the spin of electrons in the atoms, right, through what we call spin orbit coupling. Right, and so that means that we have 2 angular minimum we have to add. We have to add the orbital angular minimum of the electron around the proton, as well as the little spinning top that is the electron. Right, the electron's always spinning at some angular minimum 1/2. It's always spinning because of spin. Right, so we have a little top that's rotating around a larger circle that's itself the top, right? So we have a little top inside of a top. And we came up with a notation to describe these states, we call term symbols, right? Which had this formula like this, these term symbols. And I won't go through the rules again, but for hydrogen, I'll just write it. For hydrogen, if we look at hydrogen, again, what we know from hydrogen is that there's one level at n equals 1, the 1s orbital. There's a 2s orbital and then a set of 2p's. Right, that's our kind of basic structure of hydrogen. This is just orbital angular minimum, right? Just the L, if you will. And then we couple it to the spin, and that causes the states to split. And the N gets, the 1s gets lowered to an energy, and we write that term symbol as the doublet 2s, 1/2 state. Right, L is 0 for this. This is a 1 here, right, for the n equals 1. Right, and it's an S because it's L equals 0, and it's 1/2 because J here is L plus S. S is 1/2, L is 0, so the total angular minimum is 1/2. And then the N's also split into 3 states instead. You have a 2, n equals 2, 2s 1/2 state, right? That's the 2s state. And then the p state split into a doublet, where you have the 2p 1/2 state here. They're the same energy, or at least we think they are. Turns out they're not, but we won't talk about why they're not. That's a much more complicated concept, but in fact they're not degenerate. There's a small splitting, and that's actually it's due to relativity. It's due to the fact the electron and the proton they're moving at, when you account for the fact that they might be moving near the speed of light, these actually split, which is kind of a cool effect. It's a very weak one, but they exist. And then there is the higher energy 2p2 3/2 state, right? Where you add L was 1 for P and you add 3/2 to it instead of subtract. Okay, and so we have transitions between these states. And the question is what, but some of these are allowed and some aren't. So if we look at the spectrum, we would expect to see between these three lines, we would expect to see lines corresponding to this transition, and maybe between the states, these transitions as well. So we would expect to see 3 lines. But in fact, you don't see all of these because some are forbidden. Not all transitions are allowed. All right, we kind of talked about this idea of something being allowed or forbidden with the particle in the box. We talked about it very briefly. We talked about dipoles and electric dipoles. I won't go through that math again. What I'll tell you is the results of it. But only certain transitions are allowed. And so for atoms, we call these selection rules, right? The rules that tell you which transitions you'll see in your spectrum or not, which ones are intense and which ones are zero, right? Which have the zero intensity, which ones do not. We call that allowed or forbidden. So allowed, I'll just write that are transitions with non-zero probability or intensity, however you want to think about it. Right? They show up as an absorption, and forbidden is the opposite. Zero probability. Right? So we calculate an integral to calculate the probability of that transition. How likely is it from a state of electron here to go here, given enough energy? Some of them are zero, some aren't. There's a very set of specific rules. And we'll see these rules time and time again when we get to molecules as well. The first biggest rule of them all is that the total spin can't change. All right, we'll see this in helium. Helium will come up that there's actually, where the spin is, your helium has 2 electrons, there's 2 options. The electrons can be like this, spin up, call that a triplet, or they can be like this, against each other. We call that ortho and para, or spin up, or singular triplet. We'll look at that when we get to helium. But you can't convert between the 2. All right, so what that means is that a state that looks like this cannot transition into a state that looks like this. Right? You can't flip a spin. This rule is broken a lot, but by basic law, by basic physics, basic quantum mechanics of what we've learned so far, this is a hard rule. Right? There are instances where this rule is broken, and in fact, it's broken in phosphorescence. This rule is broken in phosphorescence. The whole reason phosphorescence exists is because a singlet can do this. There's a weak probability of it non-zero. But this is kind of like the hard rule. Another one for the hydrogen atom is that L has to change by plus or minus 1. Okay. For other atoms, multi-electron, L can either be 1 or 0. So it can either be 0 or plus or minus 1. But for hydrogen, the L has to change. What that means is that you can't go from an S state to an S state. You have to go to S to P or P to D. Right? You always have to change angular minimum by 1. This rule is hard. Hard is a hard rule, and there's a really, really interesting reason why it is. And it's just mathematically this delta L equals 0 is a no-go for hydrogen or any single electron system. You can't do it. The math always works out that the probability is 0. You'll never break it. So L always has to change. So what this means is that S to P is allowed, but S to S is not. Okay. And the last one, which is related, is that when you include spin, delta J has to be either 0 or plus or minus 1. So it can't be any other values. So J can change, L can't change, or L has to change. All right, so let's look at these 3 transitions that we've written down for hydrogen. So So I'll just rewrite them again. All right, the 3 n equals 2 to 1 transitions. So the first one is the 2s to 1/2 to the 2 to, the 1 s 1/2 state. That's this one. That's not allowed, forbidden, because it's s to s, because delta L is equal to 0. Right, so you're never going to see a state where it goes from the 1s orbital to the 2s orbital. It's completely and utterly forbidden, even if we don't include spin-orbit coupling. If we just look on this side and we calculate the probability going from 1s to 2s, it's 0. Can't do it. Right? It's got nothing to do with spin. So that's a hard rule. Right? So if we looked at the hydrogen atom from this perspective on the left, the 1s, an electron in the 1s orbital could go into the 2p orbital, no problem. That's fine, but it can't go into the s orbital. So, but we could put the system in the p 1/2 state, this one right here, the one that's degenerate with the s orbital, and put it and relax it back into the ground state. This is the line, right? Because delta L is 1. So imagine that we put an atom in this s 1/2 state. Imagine we prepped it into that system. It can't do anything. It can't relax. If an atom is put into this state, there's no way it can emit any energy to go relax to the ground state because the transition is forbidden. So in some ways, this 2s 1/2 state right here is like a place where it gets locked. It kind of gets trapped. It's like a trapped spot. And there are lots of these. There's lots of trapped spots in atoms and molecules where molecules will get stuck into these regions, into this state. Maybe you put the system into that state from another place. So for instance, maybe I do this. Maybe up here in the p's, the 3p orbitals, that'll split into 2p 3/2, and 2p 1/2. Imagine I have a system in this state, my electron's here, and then it relaxes down to this state and it's stuck there. Right? This transition is allowed because L is changing. J is 0, that's fine. It could also come from here as well into that S state. And then when it gets in that S state, it can't go anywhere else. So it always retains that energy. It doesn't drop back down into the S 1/2 state because it's forbidden. It's always 0. Now imagine if this is fast, there's a high probability of taking something from this n equals 3p state, putting it into the n equals 2s state. That's totally allowed. Right? I could go like this. Right? I could take a ground state atom, put them up here, and then travel down this way. And any atom that gets into here gets stuck. Right? And maybe there's some slight reason why it's allowed for it to transition back to the ground state. It's much slower. This entire process is what lasers do. Lasers the idea of a laser is you're pumping it up to a state where it gets stuck at high energy, and you slowly whittle that energy out through a very rare transition to a ground state to create a loop like this, right? And eventually, once everything in this state goes down to here, you've done your process, because we're actually doing this. So you can go in a loop, but there's a place here where it gets stuck. And so if you have a lot of molecules that start here, you can put them up here easily, and then you quickly relax here, and they get stuck. So you can transfer all of your population from here into this excited state. And then slowly they get excited and relaxed and release photons. And that's exactly how a laser works. Right? This is what's called population inversion. So as I do this process and excite electrons, I'm funneling them from the ground state into this trapped state here, the 2s state, the n equals 2s state. And then they slowly relax, much more slowly than the other parts of the loop. Right? And that's actually how a laser works, right? The lasing frequency that you would get, the thing that you would detect, the laser light that would come out, is the light being released by this forbidden process, right? This slow process. Photons will slowly leak out of your trapped atoms, and they all do so in the same direction, and that generates your light. This will be your laser light, right? So you can actually build, it's not a very efficient way of doing it, but you can build a laser of hydrogen atoms in this regard. by using these trap states. Okay, so that's one of the powerful things about forbidden transitions is that sometimes you can break them. You can break the forbidden rules. But typically when you break a forbidden transition, you break the rules. Those are so rare that any system, any atoms in that excited state, only occasionally in a very slow kinetics will release photons and relax to the ground state. Okay, so anyway, I digress. So we've looked at these two. This is the n equals 2 transitions. Of course, there's another one where it's the 3/2 state into the 1/2. And this is also allowed because delta L is equal to 1 and delta J is equal to 1. J changes by 1 and L changes by 1. So these are allowed. So we have 2 allowed, 1 forbidden. There's one more we haven't considered, which is the transition between the 2 p states. Right here, this must be forbidden though, because delta L is 0, even though delta J is 1. Right, so we predicted there are going to be 4 transitions here, but only 2 of them are allowed. Right, so if we were to calculate these frequencies and go look at our spectrum at those wavelengths or the frequencies, however the energies of those transitions, you won't see anything. It'll be completely, they'll either be super dim because they're only slightly allowed by some effect we haven't considered yet, or they'll be invisible completely. And we would only see 2 bright lines, and they would correspond to these 2 transitions right here. And these 2 transitions are the Lyman alpha transition. Right? This is what we call the n equals 2 to 1 transition. Right? That's what all the old astronomers saw and all the old physicists saw. But it's actually a doublet, and this is the doublet. Right? It's the 2 allowed transitions between the n equals 2 and the n equals 1 manifolds. Okay, we're going to, as we go to molecules, we're going to see rules like this time and time again when we get to vibrations. Vibrations will have a specific set of selection rules. Rotations have a specific set of selection rules. And electronic transitions in molecules, exciting electrons from one orbital to another in a molecule, have very similar rules like this as well. Right? And they tell us what's bright and what's dark. Right? How can we move energy through a molecule? Right? This is telling us there are certain pathways, if you will, and there are some pathways that are not allowed. Okay. I have one more comment I want to make about atomic states before we move on to helium. And the question is, what I've described to you is how can we move energy from one state to another. But the one thing that I haven't described yet is why do I order them in this way? Why is this state lower in energy than this one? Right? Because I didn't actually specify that. I haven't given you a formula for the energies. I just wrote it down that the 1/2 states are here and the 3/2 state is higher in energy. But how can I determine that? And it turns out there's a set of empirical rules that give me the answer to this question, right? Which states are more favorable, higher in energy or lower in energy? Right? And these rules actually apply to molecules as well. They have a slightly different approach to molecules, but the rules are similar. These are what's called Hund's rules. And these specify effectively how do we put electrons into a system, right? Obviously, electrons will go into the lowest energy states first, right? What are the lowest energy states? How can we define them, right? How do we order the term symbols in terms of energy? And they're actually pretty simple. There's 3 of them. So for the first one is easy. For a given electron configuration, the term of greatest multiplicity, I'll define this in a second, lies lower in energy. All right, let me give you an example of this rule, and I think it'll become more clear. So let's look at carbon. There are two different ways to build carbon's electron configuration. One s2, two s2, and then we have 2 electrons left, right? There's 6 electrons in carbon. We could have 1 electron in one p orbital and 1 electron in another. Right, so that would be look like this. Something like that. You could have something like that. Or we could do it like this. Right, we can put them all in the same orbital. Right, so that would look like this. And the s orbitals are filled, and then we fill one of the p orbitals with a pair. So now let's calculate the term symbols for these. Okay. So here's the first one. We have 2 electrons in the p orbitals. So the first electron's angular minimum is 1. The angular minimum of the other electron is 1, right? Because they're both in p's. Right? So that means that L total is L1 plus L2, which is 2. Okay, and what's the spin here? Well, the spin is 1/2 plus 1/2. Right, we add the electrons together, which is 1. All right, so J here is 3. Right, L plus S is 3. So the term symbol for this is going to be 2s plus 1, which is 2 times 1 plus 1. That's 3. We call that a triplet. L is 2, so it's a D. And we have J equals 3. Right, so this is a 3D3 term symbol. Okay. Now let's look at the other one. This one, let me do it with a different color so it's easier to see. So again, L1 is equal to L2, which is equal to 1, right? They're both in the p orbitals. But spin here is 0, right? Because one spin up and one spin down. So it's half plus minus a half, so it's 0. So this is a singlet D, J equals 1 state. Right? And what we mean by multiplicity is total spin, is spin. Okay? So the state, the 1s, where we put the electrons in separate orbitals and they're matched in spin, we call that the multiplicity of that is higher. It's 3d3. Meanwhile, this one is singlet. So this is higher in energy, the singlet, and this is lower in energy, the triplet. The way you can justify this is that there are 3 different ways to write the p orbitals here. We can put the electrons in any of the other 3. Right, so there's a multiplicity of 3 in the singlet, if you will. Right, there's 3 different orbitals to put 2 electrons in. So there's 3 different options, if you will. How many options are there for the triplet? Well, there's this one, this one, this one, this one, and then there's another set of 3 where they're all pointing down. So there are 3 versions here, and there are 6. So this has a higher multiplicity, which means it has more like permutations, if you will, and that means it's lower. So more possible electron permutations equals lower energy, right? Just by this one rule, I can predict that the carbon electron the carbon is in a triplet D state. Right? That's lowest energy. In fact, that's the case, right? If you remember from Gen Chem, the way we filled the we filled the valence shell of the atoms in the second row was we put the electrons in one by one in each of the separate orbitals, not pair them together, right? And that's due to Hund's rule number 1, right? That the spin is always the higher the multiplicity, the more options there are to put electrons in a set of orbitals, generate options, if you will, different choices, the lower energy it is. All right, 2 more. a given spin multiplicity, so fixed 2s plus 1, right? A term with the highest value of L lies lowest in energy. Okay, so example. If you have a choice between a 1d2 state versus a 1s0 state, 1d2 will be lower energy. Simple stuff. Simple rule. And the one last one is for atoms with less than a half-filled valence shell, right? So for instance, carbon is, because the two P's are not half-filled yet, right? There are eight places to put electrons in the valence shell, and there's only 4 electrons, so it's not over half-filled, or less than or equal to a half-filled valence shell. The lowest value of J lies lowest in energy. Meanwhile, for atoms with more than a half-filled valence shell, so oxygen, for instance, or fluorine, the highest value of J lies lowest. Therefore, for example, in hydrogen, the 2,2p 1/2 state is lower in energy than the 3/2 state. But in fluorine, the 3/2 state is lower in energy. Than the 1/2 state. Okay. These 3 rules allow us to predict the electron configuration for any atom. All right, by Hund's rule 1, you can figure out where the electrons go and where they fill. And in 2 and 3, it'll tell you whether it's a singlet or a triplet, what's the lowest energy angular minimum state. Right, so we don't even have to worry about p orbitals and d orbitals or anything like that. Right, this is just arithmetic with numbers, right, and just a couple of rules. And you can identify exactly what kind of state your atom is going to be in the ground state, what the ground state looks like, and that also allows you to predict what transitions are allowed, right? It allows you to predict the spectrum. If you know what states lie lowest in energy, then you know what the fundamental transitions of your molecule are, right? So for instance, if the ground state is a D state like this, all the strongest transitions you're going to see are ones where it goes to P or F. But there's not going to be any transition to an S state because that's delta L equals 2, and that's forbidden. Right, so this allows you to build up predictions for the atomic spectrum. It tells you how to arrange the electrons as you fill orbital shells. And it tells you what kind of states are stable. It gives you a sense of what the atom looks like. And this is a big deal because when we get to helium, I'll show you that knowing what the multiplicity is, that in fact helium can exist in 2 different forms, one where the spins are matched or matched, and one where they're mismatched, and they almost exist like totally 2 different atoms. They can't communicate to each other. So you can have atoms that look like this, helium atoms look like this, And there's no way to ever convert between the two because that would be delta S equals 1. Right? So helium, in fact, is in some ways is not really one atom. It's actually two atoms. Two atoms with very, very different electric properties. Right? Let me show you that. Again, let's just draw a very simple electron diagram for helium. We'll just do the helium, the 1s orbital, 2s and the 2p's. Right? And there are two options to draw the electron configuration for this. One is the way that we know and love. Right? This is a 1s0 state, right, where both the electrons are paired. Right? But there's a completely valid way to write helium. It's higher in energy. It looks like this. Or it could look like, right? Or there's also another option. Like that too. Right? So let's calculate the term symbols of these. So the term symbol for this one is a triplet, right? 2s plus s, your total spin is 1, right? 1/2 plus 1/2. So this is a triplet. It's an S state. And the total angular momentum is 1. Right? Because you have two 1/2 spins. And this one is a singlet S state with 0. Right? And what Hund's rules tell you is that this is highest energy. Right? Because you have an electron in the 2 orbital. That obviously costs some energy compared to this. But the spin multiplicity compared to this one is lower. So this one's higher energy. This is intermediate. And this is ground. Right? So this is, again, this is what you would learn in what do you call it? In general chemistry. But there's a perfectly reasonable atom that exists like this. Helium atom that exists like this in the triplet state. The important thing is, of course, it's higher in energy. We could calculate what the energy difference is. But the amazing thing about the really cool thing about this, I think, is that oh my god, these are just all falling apart. All right. So if our 1s0 state is here for helium in energy, the 3s1 state is obviously higher in energy because you have to promote an electron to the n equals 2 state. It must be higher. Like that. Right? So imagine I have an electron here. Right? Imagine I prepare an electron in this state, system in this state. All right? My system is sitting in this state. Well, not an electron, but let's say my helium atom is here. Right? Now it can do all sorts of transitions, right? It can get excited and go to the 3. Well, let's think about what it could go to actually in a second. Right? But it has its own set of transitions to go to. What can this go to? Well, let's think about where this can go. What kind of excited states does it go to? Obviously, you can't take an electron and put it here. Right? So this state, for instance, right? So there's this next state. We'll call this the 1, and then there's the 2 1SO here. Again, that's this state right here. But that's forbidden. That's not allowed. Can't do that by the selection rules. So the only state, the next state that the ground state can access is if we put this electron here. Right? And what would the term symbol for that be? Well, spin is 1. So spin is 1, and total L is 1. So J is 2. So this is a triplet P2 state. So up here somewhere, there's a triplet P2 state. But what's the problem with this? Well, that doesn't work either because now delta S is 1. So that doesn't work. But there's another state where I can put it like this. That's a singlet P1. I don't know where the energy is, but actually we know because it's more than half, the valence shell is more than half full, and the larger J has a lower energy. So the singlet has to be up here, and that's the first allowed transition. Right, that one's allowed, right? J changes, L changes, right? We're all good. Right, so there are two states that are in this region that we've predicted that you can't see. You just avoid them completely. There's no way to contact them. Right, a ground state will never see these states. So you can only access the fourth excited state, if you will. Right, and so now let's think about this state right here. Well, the most important thing is that this can't happen, right? It can never go over here to the singlet state, right? Because delta S is equal to 1. Right, we can't flip a spin. So that's impossible. Right? This is explicitly forbidden. Now, what states can this access? Well, it can't access this state, right? Because spin changes. But it could access this state, right? So the important, and if you just keep doing this logic, you'll see that this connects, that the singlet states, which is 2s plus 1 equals 1, or s equals 0, and the triplet states are completely separate. Completely separate. You can never convert a singlet into a triplet. So it's very likely you can absolutely create this atom, prepare an atom in this state, and it will never, ever relax to the ground state because it's forbidden. Right? So in fact, there are two types of helium. There's what's called orthohelium, which is S equals 0, and perihelium, which is S equals 1. I think that's the right. I might have those flipped. I think that's right. I might have them flipped. But anyway, the point is that there's two different types of helium that have very, very different energetics. Right? They exist in entirely different spaces. Right? They can't communicate with each other. They all have allowed transitions to completely different energy levels. They exist in entirely different spaces. Right? There's no reason to consider them the same atom other than that they have 2 electrons and 2 protons. Or 2 electrons and 2 protons. Right? So this is like this, and this is like that. We tend to write it, right? The pair and the mismatch. The mismatched and the matched spins. Right? And these can't communicate to each other. Cannot interact at first order. There might be ways to break this, right? But we're not worried about that. They're very rare. But there might be ways to convert between the two, but they're rare and they're likely forbidden. Right? So in fact, helium can be formed in 2 completely different ways. And so helium in its triplet state, right? We always expect helium to not be reactive, right? We expect helium to not be all that interesting, right? Because the spins are paired. You have a full valence shell, right? It's a noble gas, right? As boring as you can imagine. But this other helium, the perihelium, has unpaired electrons, not a full valence shell. In fact, it doesn't even have a full core shell, right? This thing's quite reactive, right? Even unstable. And this is a noble gas. Right? 2 very different atoms, very different characteristics. Right? But there's no reason to assume that helium is one or the other. Right? You can absolutely prepare them in 2 completely different states that are completely different atoms with different reactivity. All right, when we get to molecules, this will happen all the time. We're going to have to deal with singlets and triplets and anything with fluorescence and phosphorescence and electron transfer, things that happen in photochemistry. Any sort of photochemistry has to do with dealing with singlets and triplets. Right? There are going to be molecular states that are singlets and some that are triplets, and sometimes they'll be really, really close in energy. In fact, the molecule might even be a resonance between the two, that they're so close in energy that There's an equilibrium distribution between singlet and triplets. And they have very, very, very different reactivities because their electrons are paired differently. Right? If your molecule has all of its electrons paired, it's not really interested in doing anything. But if you have a system that can be prepared in a state where the electrons are unpaired, and it is built up in such a way that it can't go back to a non-reactive state. Right? Remember, these are locked in place. They can't talk to each other. So if you can prepare a molecule where the electrons are unpaired like this, the reactivity of it is very different. Right? Very, very different. Right? And you see this all the time in biochemistry, photophysics, and anything you can do. We'll look at those as we go through molecules, some examples of this. Okay. That's kind of all I want to say about spins and states and stuff for now. I want to talk a little bit about helium. Right, and I'm going to, unfortunately, have to be the bearer of bad news. I'm not going to be able to think about helium very well. So we're going to hit a roadblock. But luckily, the roadblock will give us an option. It'll say, well, you can't solve this exactly, but maybe you can come up with a way to do it, to approximate things. All right, we'll see how far we get through this today. Oh, my notes are over here. Very good. So what I want to do is I want to build up a Schrodinger equation for the helium atom. I want to do the same thing we did for the hydrogen atom, but for helium. All right, but now we have 2 electrons. Right. So let's build an axis system to think about the motion of all of our moving parts. All right, so I'm going to put my nucleus here in the middle. So there's 2 protons here, and for helium-4, there's 2 neutrons here as well. Here's my 4 helium nucleus. Okay, and then I have 2 electrons connected to it, right? So let's put 1 electron somewhere. All right, so there's one of my electrons. We'll call that electron 2. Right, and we're going to give it a vector, just like we did before, R2. And then I got another electron floating somewhere in space. We'll call that electron 1. And it has a displacement vector R1 from the nucleus. Right, and I'll define the angle between them as theta. Okay, so this is, and then we have one more term we have to consider, right, which is the distance between the 2. Right, so we'll call that R12, and that's the absolute value of R1 minus R2. Right? So we have a couple of things to deal with. We have to deal with the attraction of electron 1 to the nucleus. So let me write that down. Let's just write down all the terms we need. First, we need the kinetic energy of E1. So this is like an energy accounting. Right? We're going to account for all the terms in the energy, right, which is what we always do. Right? So we need kinetic energy of electron 1, kinetic energy of electron 2, we need the attractive potential energy of the nucleus and electron 1, right? That's the attraction along R1. Right? Of course, they're attracted to each other, just like in the hydrogen atom. We need that for the other electron. Nucleus to electron 2, that's R2. We have a new term, though, right? So far, all I've written are kinetic energy plus potential energy of the electrons. That is, it's basically 2 hydrogen atoms put together, right? All the hydrogen atom was just a kinetic energy plus potential energy. Now we got 4 terms, or 2 pairs. We got 1 extra term, the repulsion between electron 1 and electron 2, right? That's the R1 minus R2 term. Right? So there's a new term in our Hamiltonian. We have basically 2 hydrogenic electrons orbiting around the nucleus, just like in the hydrogen atom. just 2 times it, but then we have this extra term, this repulsion term. So let's write it out. This is page 55. So the Hamiltonian for this looks like the Hamiltonian for electron 1 plus the Hamiltonian for electron 2 plus the Hamiltonian for the interaction term, which is the repulsion, EE repulsion. All right, so these two look like hydrogen atom terms. I'll write them out more explicitly. And then we have this new term, right, which is due to the repulsion of the 2 electrons together. So I'll write the kinetic energy of the first electron. I'm going to write some notation for you here real quick. The upside down triangle squared. It's just the second derivative term with respect to position. I just don't want to keep writing this. So one of the notations that mathematicians use for this term is what's called del squared. Del squared. So I'm just going to write that here. And that's for electron 1. All right, so that's the kinetic energy of electron 1 minus the kinetic energy of electron 2. And then we have the potential energy of electron 1 to the nucleus. So that's going to be the Ze squared over 4 pi E naught times 1 over R1 minus Ze squared over 4 pi epsilon naught 1 over R2, right? These are just the attraction of the nuclei to each of the electrons. And then we have a new term, which has a different sign because it's a repulsion, not a 4 pi E over minus the distance, right? Okay, so this term, this is just 2 hydrogens smashed together. And this is a new term for E-E interactions. Okay. So now what I have is an expression for my energy with respect to the position of electron 1 and respect to the position of electron 2. But the problem is I also have a term that's dependent on both, dependently. Right? This term right here is dependent on the position of R1 and R2. Right? So depending on where R1 is, it changes where R2 is going to be in order to minimize this term. Right? If imagine electron 2 is fixed by itself, right? It's sitting here, and electron 1 starts to come in towards it. Well, in terms of minimizing the energy, electron 2 is going to want to move away. So R2 is a function of R1. So R1 is a function of R2 and vice versa. Right? They're coupled. So my Hamiltonian now are 2 sets of terms that are separable, right? We have a term in terms of electron 2 and a term in terms of electron 1. They don't talk to each other, right? They're all dependent on the position of 1 or 2. And then we have a term that's dependent on both. It turns out, due to this 1 over R1 minus R2 term, this equation, H psi is equal to E psi, right? Applying the Schrodinger equation to this is not solvable. Right? We can't come up with a solution for it, exact solution. Right? The moment you get to 2 electrons, right? The only thing we can solve exactly are 1 electron systems. Because the moment you get to 2 electrons, you have a variable, a coordinate that's dependent on another coordinate that is also dependent on the other coordinate. Right? So you have 2 coordinates explicitly dependent on each other, and that just makes the math go crazy. There's tons of solutions to this problem, or no solutions at all, actually. There's no solutions at all. So we can't do what we did with hydrogen anymore, which was solve the Schrodinger equation, get some wave functions, get some energies. Obviously, there are wave functions that satisfy this. Obviously, the helium atom has energies. But there's no mathematical way to explicitly write them down. There's no explicit solution. All right, and this was a real scary problem for physicists because they're like, you know, the early chemists, because they solved the hydrogen atom, they figured out everything to know about the hydrogen atom. Super great. And then they go to the next simplest thing, which is the helium atom. Just add one electron and a couple of neutrons and a proton, and the whole thing falls apart. You can't do it anymore. So what we have to do is we have to make an approximation somewhere. All right, we have to simplify it in order to make it solvable. So what I'm going to do is, let's do the dumbest thing possible. Once I find a formula for it. It's 57, so 56. Oh, it's over here. Of course, I just leave it over here. Okay, so what I'm going to do is this. Where can I put this? Let's put it over here. Let's turn off. So let's assume that the repulsion term is small. Okay, maybe they don't really interact with each other that much. They're fairly far apart. Maybe we can just neglect it, right? That the attraction between the nuclei and the electron is very large, and that the repulsion is small. So let this term go to 0. Okay. So what happens when we do that? Well, this term goes away, and what we're left with are just two hydrogens smashed together, right? We have two electrons acting independently. Okay, two electrons acting independently, right? And we can write the wave function for this as a product of hydrogen wave functions. All right, we take it as a product. All right, we can separate the equation into two equations. We have an energy term for the electron 1 and an energy term for the electron 2. We solve them separately, and that leads to a wave function that's a product, like this. Seems like a reasonable thing to do. Right, we're just thinking of a helium atom as two hydrogens put together. And so what we would expect is that the ground state wave function looks like the 1s orbital centered at R1 times the 1s orbital centered at R2. Right? That seems reasonable, right? This gives us the electron configuration we want for helium. All right, we have an electron in the 1s orbital, one in another 1s orbital. They're both sitting there together. Okay. And the energy formula you get from this, go ahead and start erasing this. I'll get rid of this too. The energy you get from this, so the energy of the helium atom for this, is just 2 times the energy of the hydrogen atom. Well, you get En1 and En2. Right? You get an n quantum number for each electron. Right? Each electron has its own set of quantum numbers, and the energy is just the sum of the hydrogenic energies. Right? So these are just hydrogen energies. And so that's going to be equal to is equal to z squared times minus 13.6 eV times 1 over n1 squared plus 1 over n2 squared. Okay, so z here is 2. Z is 2 because a helium has 2 protons. So this is equal to 4 minus 4 times 13.6 eV times 1 over n1 squared plus 1 over n2 squared. Okay. All I've done is I've just jammed two electrons together like hydrogens. So we have two hydrogen atoms overlapping each other with two electrons acting independently. All right, and then you end up just getting a sum of hydrogen energies. And so now let's calculate the first ionization energy of helium. How much energy does it take to kick off the first electron? Right, so that's going to take n1 to infinity, and we'll let n2 be 0, or stay at 0, or sorry, stay at 1. Sorry, excuse me. No, actually, let's not do that. Let's do the second. Let's do the second, so both electrons. Right, so this is going to be He goes to He2 plus 2 electrons. Right, we're going to kick them both off. Let's see how much energy that costs. So we're going to both send them to infinity. Okay, and that energy ends up being minus 2 squared, well, 2 squared times 13.6 eV times 1 over 1 plus 1 over 1 squared, which is minus 8 times 13.6 EV, and it's about 190 EV. Right? So it takes 109. We predict that by doing this approximation, it takes a little over 100 electron volts to kick off both electrons. All right, so now let's go do the experiment. Let's go measure. This is an experiment. How much energy does it take to both electrons to go away? And the energy of the ionization is minus 79.0 eV. And we're off by almost a factor of 2. So I would call this a terrible guess. Right? Remember with the hydrogen atom, we got everything perfectly. Right? Hydrogen atom, we can calculate every energy with exact precision, up to how well we know the constants. But here, by assuming that the electron-electron repulsion is small and getting rid of it, we're so far off, we're not even close. Right? There's another 20 eV of energy. That's more than the energy it takes to remove an electron from hydrogen. Right? So there's a ton of energy difference here. Right? Almost a whole ionization energy worth of energy that we've missed. Right? So that must mean that electron-electron repulsion is significant. All right, so our approximation that helium is just two hydrogens put together is obviously not good. So how can we do better? How much time do I have? Yeah, I think we can get through this. All right. So let me suggest a very simple fix. So we'll get through this in 20 minutes. Let me get my other page out. Oh, here it is. Very good. 57. Yeah. Okay, so the way that I wrote this wave function is a product of two wave functions, right? Two hydrogen wave functions, right? These are hydrogenic. Right, just like this, right? That's the way we wrote this, right? We call this a direct product. What happens if I swap the electrons? Well, what do I get? Well, I just replace R1 with R2, and R1 with R2, and R2 with R1. Well, electrons are equivalent. are identical and equivalent. So these are the same thing. It turns out that this is not appropriate behavior for an electron. This is not physical. All right, so we've actually, our problem with our guess is not just the fact that we neglected electron-to-electron repulsion. It's that this idea that you can swap, that the wave function's even upon exchange, symmetric upon exchange of electrons, turns out to be a bad approximation. In fact, it's not what electrons do, because they're fermions. So I wanted to write this, 56, 57. Instead, fermions must satisfy a different property. Right, so when we exchange the electrons, right, we just swap them. We don't get the same thing back, but it changes sign. So we say that this is anti-symmetric upon exchange. Okay, so what the problem is that our wave function, when we derive it as a direct product, doesn't satisfy the property of a fermion that when you exchange them, that the sign has to flip. You get an inverse sign. Right? This is fixed. All fermions exhibit this property, especially electrons. Right? And this actually comes from the idea that electrons can't exist in the same space and they have to be opposite spins. The only way for that to be satisfied is for this to be true. Right? So this is literally saying the same thing, that electrons can't exist in the same space. This is the mathematical equivalent of this. Right? So this is what we call the exclusion principle. And the exclusion principle is that you could say that electrons of the same state can't exist in the same space, or you could say they're anti-symmetric upon exchange. Exact same state. But our wave function guess that we guessed, right, this direct product, doesn't satisfy this property. Right? So that's a problem. We want it to satisfy this. So we need to come up with a new wave function, a new guess wave function that isn't a product, a direct product, but rather one that satisfies this anti-symmetry rule. We need a new guess. So new wave function guess. Right? We can create whatever wave functions we want from the completeness postulate. Right? If we have a set of equations that satisfy the Schrodinger equation wave function, we can create new wave functions with sums and differences of them. So if we have some wave functions that satisfy h psi equals e psi, we can construct new wave functions such that the new wave function is a sum over the other wave functions. I got to add some coefficients to it as well. Right, this is completeness, right? So if we have these hydrogen orbitals, right? Hydrogen orbitals. We can create new orbitals by just summing them, right? We can basically make new wave functions with sums of wave functions. And what we need is we need a new wave function that satisfies this property that when you exchange the electrons, that you change the sign of the wave function. Right? That's all that's happening here. It's odd. It's an odd symmetry. So there are 4 possible combinations to choose from. So what I'm going to do, actually, let me go back to this for just a second before I start this. I want to define a new system. I want to define notation. Define a spin orbital alpha if the electron is plus 1/2, and beta if electron is minus 1/2, such that the integral of alpha alpha equals integral of beta beta is 1, and when we multiply alpha and beta together we get 0, right? This is just the Pauli exclusion principle, right? This will satisfy it that if you have two electrons of different spin, or two electrons in the same region with different spins, they cancel out. So our wave function is going to also have these spin orbitals attached to it to define whether the electron in R1 is spin up or spin down. Right? So we're going to multiply these by alpha and beta depending on which one it is. So the options are of wave functions is to take our direct product and define the electron 1 to be spin up and the electron 2 to be spin down, like that. Or sorry, both of them spin. Sorry, let me start over. Both of them spin up. Right, that's a possibility. Another one is that they're both spin down, like that. Or maybe one has to be spin up and one has to be spin down. Right, so that's going to be equal to 1 over the square root of 2, psi 1, R1, psi 2, R2, times alpha 1, beta 1, plus alpha 2, beta 2. Oh, sorry, I got that flipped. Sorry, beta 2, alpha 1. Right, so this is saying that either it's in this state where it's up and down, or sorry, let me start that over again. Yeah, up and down, and this is down and up. Right, so these are both up, right? This is a triplet. They're both been down. You have a simultaneous superposition of up and down like this. Or we can calculate the difference of them. Right, it's the same thing, but now we take the difference of the functions instead of the sum of the functions. Both are allowed. Right, and so we can go through the math. What happens when we substitute 1 and 2 together? Right, when we exchange the electrons, when we take R2 and R1 and we replace them, right, we swap the indices, what we're going to find is that, well, these obviously fail. Right, if you replace R2 and R1 here, you just get the same thing again. Right, so these are symmetric. And it turns out if you do the math, 3 is symmetric as well. You can try to prove yourself to that, but if you swap R2 and R1 and beta here, the 1s and 2s here, you just exchange the electrons, you just change the indices of the electrons, you get the same thing back. Right? And so it can only be this one. Right? So our wave function has to have this minus sign in it. Right? So our wave function, the proper wave function for helium is a simultaneous superposition, 1 over square root of 2, of the singlet. Like that. This satisfies this anti-symmetry property. All right, if you do the math and you work it out, you'll see that this negative sign gives you a negative sign overall, and it gives you this anti-symmetry property. Okay? So this, again, is for EE repulsion turned off. So what I've done is the repulsion's turned off, but now I've accounted for the fact that the electrons can exchange with each other and they have the proper symmetry, right? That the sign changes when you exchange them, right? There's no difference between electron 1 and electron 2. They're exactly the same particle. They're not the same. They're identical. You can't tell them apart, right? So there has to be, in order to, there's no reason that I can't swap them because they're identical. There's nothing stopping me from doing that. These labels are arbitrary, but when you swap them, you got to get a negative sign, right? The only way for that to happen for helium in this approximation is that we treat the system like a simultaneous superposition, a difference of the singlet states, right? The spin up and spin down states, right? And that should make sense, right? We want the electrons to be paired, And we want them to be antisymmetric upon exchange, that's why the negative sign shows up. So now what I want to do is take this wave function and calculate the energy of ionization, which is taking the wave function, I'll just write it like this, times the Hamiltonian, times, right, I'm going to calculate the average energy of this state, right, by doing the usual calculation, r squared sine theta dr d theta d phi, right? So I'm going to integrate my wave function over the entire sphere and then calculate the average value of the energy, right, by using my average energy function, my average energy equation, right, integrate over the whole space and slam the operator between the wave functions. All right, we can go through this math. Right, and it's a kind of a tedious problem, and not one that I really care about the details of. Where are we? Ah, here it is. Great. And what we get again from this is minus 108.8 eV. So that hasn't changed at all. But what we can do now is we can calculate the average value of the R1, R2 of our gas, right? The repulsion term. So let's turn repulsion on with our new wave function. And we find when you calculate this, this integral ends up being this big wave function times e squared over 4 pi epsilon naught 1 over R1 minus R2 times our big wave function. This is our big wave function. This. And do all the integrals, right? And so on. Let's write d tau. So I'm too lazy to write the r squared sine theta. Right? Now I can evaluate this repulsion term, just the way I evaluate any operator, right? I just say, what's the average value of the repulsion? Right? And this actually works out to a really nice answer. It works out to 5z over 8, which is calculate and times a factor of so actually I'll erase that there. I'm missing a term. Calculates the 34 eV. So what this calculates by using this guess, right? This guess that explains our electrons. We basically made a guess for what our orbitals look like, and they look like hydrogen orbitals, but they're set up to allow the anti-symmetry, the Pauli exclusion principle, right? And this is the proper wave function that satisfies those properties. And then now I can just guess what the average values are by applying my operator into the average value equation. And I see that the energy of the repulsion is 34 eV in this guess. Right? So all we've done is we've guessed that the wave function looks like a properly symmetrized set of two hydrogens slammed together with the proper symmetry. And I see 34 eV. So the total energy is going to be minus 108.8. Right? This is the term without repulsion, plus 34 eV. And this is equal to minus 74.8 eV. Right, and what did I say the original value, the correct value was? Did I erase it? I think it's 79, right? 79, right. So experimental is 79 eV. So we've gone from being off by 40 eV, and all we've done is we've properly dealt with the physics of two fermions. That when they exchange position, they have to change the sign of their wave function, right? This is just a product of the fact that they can't exist in the same space. All right, and then what we do is then we just use that as a guess. We say, okay, this is the right. Let's just approximate. This is our guess wave function. We build up these wave functions as hydrogenic wave functions. We're saying, okay, it kind of looks like two hydrogens together. Let's calculate the correction due to repulsion using that guess. And because we've made our guess correctly, the right symmetry, we get a value that's very close to experimental accuracy. But there's still almost 5 eV we've off, right? Right, so we're still not there yet. So, but what we've done is the best we can do right now. We've assumed that the helium looks like two hydrogens put together. We give it the right symmetry here to the fermions, right, the spin statistics as we call it, and then we evaluate the energy. We get much closer because our guess is more realistic, but we're still off by a little bit. And the question is how do we make this up? Right? How do we do better? Well, the fact of the matter is that what we've assumed is that the helium atom, the helium orbitals look like hydrogen ones. And in fact, they don't. They look a little different. In fact, what we might want to do is to think of an electron orbital instead of being a 1s, but maybe we want to put a little bit of 2s in it, and maybe a little bit of 2p in it. Right? That in fact the hydrogen 1s, the helium 1s orbital actually kind of looks like a little bit of 1s, a little bit of 2s, and a little bit of 2p. Right? We start to add more terms into our guess, and the difference between these gets closer and closer and closer together. Right? So what the instruction that I want to give, I'm out of time, I'm sorry. I just want to make one more statement, which is what I've done is a tactic that every chemist uses, because the moment we get to 2 electrons, the entire system breaks it down. Right? There's no way to solve these equations exactly. So what we do is we make the simplest guess, or what we think it looks like. Right? That our electrons exist in hydrogen-like orbitals. We make sure that all the physics are right, everything's worked out, all the algebra. And then we make a guess. We just go calculate it and see if we're close. And if we're not close, well, then that means we have to come back and make our guess a little better. All right? And then we put it back in. Make a guess. Get a little closer. Bring that result in. Modulate, right? We do an iterative process where we correct the wave function guess as we start to improve the energy. Right? So as the energy starts to get closer and closer to the real value, we get better and better guesses for our wave function. So there's this iterative loop. Right? We'll see that more often as we go through the class. When we get the molecules, it'll be very important. So we'll talk more about that after spring break. Okay, that was a lot for one day. I apologize. So there's a problem set up right now, totally optional. It's due after spring break. There's 7 problems on it. You can turn in up to 5 of them for extra credit, up to 50 points. Not obliged. They're all atom problems, and I'll make sure Sean has the answers to them at some point too. So have a good break, everybody. Yeah, thank you.
I have a question.
Yes.
What does that say?
Oh, yeah, so this R squared, this is just this, I'm just writing tau. So it's actually
okay.
this thing. It's just the integration index. Yeah. Just the generic number.
Thank you.
Thank you.
Tonight's the first night we have a full roster though. Like a few
Oh, good
weeks,
for
so
you.
maybe
We haven't had 25 in over a month.
Really?
Yeah.
Like you just haven't had raid night, or is it
No, we've just been running 22 or 23 people.
Really? Yeah, last week we ran 22. We were down a few DPS, so we didn't do any hard modes. It sucks.
Okay, yeah. So we've actually done 4 hard mode bosses, and none of them at 25 people.
Really?
And that's very common for us. We're very well known for, or we've made a name for ourselves for finishing content with a substandard number of people.
I guess Freya's kind of easier with less raid healing to have to do.
Yeah, that's right. And Thorum's pretty easy, and
Yeah.
Hodier's pretty easy. We got all of those down. Yeah, we beat Original Max with 33 people.
Damn.
Or something like that. We're really